Welcome to our first video of our statistics series. This video is going to really introduce the idea of statistics and answer the question, what is statistics? And as we start studying statistics, there is some key vocabulary that we need to be very comfortable with in order to study statistics accurately and communicate our results accurately. So the first word we need to know in statistics is what we call the population. The population is basically everything, or everyone. We usually are talking about people, but not necessarily, being studied. Maybe we're investigating college students. The population would be all college students. Number two, the second word we need to know is what we call a parameter. And a parameter is some characteristic of the population. If we're talking about all college students, the parameter might be the average GPA. That'd be a parameter of the population. When we're talking about parameters, just as a note for now, we will usually use Greek letters to represent parameters. You'll see things like the Greek letter mu or the Greek letter sigma. Something in Greek generally means we're talking about a parameter of the entire population. This is different than if I was talking about a sample. A sample is a portion of the larger population. So if I went out and said we're studying college students and their average GPA, the sample might be I took a sample of 200 college students. That would be my sample. And then with a sample, we have these things called statistics. Hence the name of our course. A statistic is a characteristic of the sample. So this might be the average GPA of the 200 college students I interviewed. And to differentiate samples and populations, statistics, and parameters, with statistics we will use English letters. These English letters would be something like what we'll call X bar, or just the letter S. So as we're looking at statistics of samples, which hopefully will estimate the parameter of a population, we're also interested in what are called variables. And these are not the variables of algebra. A variable is any characteristic of interest gathered from each item in the sample. Another way to think about the variable is it's really, when I'm conducting a survey, it's really the question that is being asked. So for example, with our college students, we'd be asking them, what is your GPA? Our variable is the GPA. And then our last word for this part will be what we'll call the data, or the actual values of the variables. So a data for our example would be something like 2.38, a 3.47, a 4.0. That is the data. So let's see if we can use this key vocabulary in an example. See if we can identify the key vocabulary. You want to know the average cost of statistics textbooks. So you survey 25 textbooks. And we're going to find and identify these key terms, these same 6 key terms. The population, the parameter, the sample, the statistic, the variable, and the data. First, the population. The population is everything that we're possibly interested in. So we're talking about statistics textbooks. The population would be all statistics textbooks. And the parameter that we're interested in studying about those statistics textbook is the average cost. The average cost. But not just the average cost, but the average cost of all statistics textbooks. Notice how I tie it back to the population, because that's what the parameter describes. That can be contrasted with our sample, slightly different. Now, our sample is the smaller group, the subset we're looking at. This is the 25 textbooks. And then the statistic has to describe that sample. It's our characteristic of interest for the sample. It is the average cost of, and then tie it back to the sample, the 25 textbooks. Now the variable, that's the information I'm gathering. The variables, when I look at each textbook, what am I recording? Or the question, what am I asking with the variable? I'm asking the cost of a statistics textbook. And the data is the answer to that question, or the actual values of the variables. So it's the actual cost of the textbooks. An example might be you find an expensive one for $235. That is a piece of data to the variable, an answer to the question. All right, now that we have some vocabulary, let's move on to an example of actually summarizing data, which is what statistics is all about. With statistics, we're often interested in what is called the frequency of an event or thing. And the frequency is just how often a value occurs. And often we'll organize these frequencies in what we call a frequency table. And to set up a frequency table, we have a little bit more vocabulary. First is what we're going to call the relative frequency. And the relative frequency is just the proportion of times a value occurs. In other words, it's the decimal equivalent of the frequency divided by the total. And often with frequency, we're interested in what's called the cumulative relative frequency. And that is the sum of all previous entries. So with that vocabulary, the way we're going to set up the actual frequency table is frequency tables will generally have 4 columns. One column for the data value, a column for the frequency, which I'll denote with just F, a column for the relative frequency, which I can denote with RF, and then a column for the cumulative relative frequency, the CRF. And so then we fill in our data values, maybe 1, 2, and so on. Actually, let's just do 1 and 2. And then we'll do the frequency. Maybe the 1 appears 3 times and the 2 appears 7 times. So out of 10, the relative frequency is 3 out of 10, or 0.3. And for 2, the relative frequency is 7 out of 10, or 0.7. And the cumulative relative frequency will start to add all the previous values. So 0.3 plus 0.7 is 1.0 for the last column. Interesting to note is the last entry should sum to 1. Now maybe if you have a round-off error, it might be 1.00001 or 0.9999999. That's okay. But generally speaking, we hope that cumulative relative frequency should sum to 1. That's all to show us how to set up the table. Let's actually make a frequency table. Let's do an example here. Let's say a baker keeps track of how many free donut holes his customers eat. $25 eat 1 donut hole. 15 eat 2 donut holes. 7 eat 3 donut holes. And 3 eat 4 donut holes. Let's make a frequency table. We have the values of 1, 2, 3, and 4 are the number of donut holes that were eaten. For the frequencies, we know 25 eat 1 donut hole, so that's our frequency. 15's the frequency for 2 donut holes, 7 for 3, and 3 eat 4. Now, if we want the relative frequency, what we have to do is divide the frequency by the total. So we need to know what the total is. And so if we add these up, we get a total of 50 customers. So when we divide 25 by 50, we get a relative frequency of 0.5. When we do 15 divided by 50, we get a relative frequency of 0.3. 7 divided by 50, we get a relative frequency of 0.14. And 3 divided by 50, we get a relative frequency of 0.06. And the fractions aren't needed so much as the actual decimal answers in our table. And then once we have our relative frequency, we can find the cumulative relative frequency by adding all the values before that. So for 1, we only have the 0.5. But then for 2, we're going to add 0.3. So we add 0.3 to get 0.8. And then we add the next value, add 0.14 to get 0.96. And then we add 0.06 to get 1.00. And that fills in our frequency table. Now that we have our frequency table, we can answer some questions about this baker. We could answer questions like, what percent ate between 2 and 3 donuts? 2 and 3 donuts have a relative frequency of 0.3 and 0.4. So when we add those together, 0.3 plus 0.14, the percent is 0.44, or as a percent, 44%. How about what percent ate more than 3? Well, I'll highlight in pink, more than 3 just means 4, so that must be this last entry of 0.06. And so we can say 0.06 or 6%. Finally, what percent ate at most 3? Well, I'll mark them in blue here. At most 3 is everybody else. I could add those all together, but what you might notice is that everybody else excludes the 6%. So it might be easier to say we've got 100% as everybody, exclude the 6% that are more than 3, and that leaves us with 94% ate at most 3 donut holes. So the big thing we're doing today is we are looking at statistics vocabulary and organizing data in frequency tables and interpreting that information. Take a look at the homework assignment that goes with this section, and in class we will investigate these frequency tables a little further. Statistics is all about the interpretation of data. So we're going to take a look today at the question, how is statistical data collected? And first we have to really understand what we mean when we talk about data. Data can be measured on several different levels. So let's take a look at the levels of measurement. Levels of measurement start with the most simple type of data and grow to the most complex type of data. It's important we know what we're working with so we make sure we can do the correct mathematical operations of it and make sense of our conclusions. The most foundational level of measurement is what is called nominal, which basically just means we put things into categories. You might say there are no numbers. So for some examples of nominal categories, you could look at color. Or maybe a yes-no survey. Do you support this political issue? Or maybe some type of label. Or gender. Those are nominal categories. Now, slightly more involved than a nominal category is something that we can actually put in order and say this one is more than that one, which is more than that one. We call this ordinal data. And that's data that can be put in order. However, with that order, there is no clear space between the data values. In other words, we can say A comes before B, but we don't really care how much before B. The space between A and B might be different than the space between B and C. An example of ordinal data might be finishing place in a race. There's a clear first, second, and third, but the space between first, second, and third is not necessarily well defined. That's ordinal. Or we might say the top 5 cooks in America. Cook 1, 2, 3, 4, and 5. That's ordinal. We can put them in order, but we don't necessarily know how much better each one is than the other. Now, when we do clearly define the space between values, we have what we call interval data. Interval data has a space between the numbers with meaning. The space has meaning. However, there still is no 0 point. The space between the two numbers is well defined, like in the example of temperature. "30 degrees is 10 more than 20 degrees, just like 90 degrees is 10 more than 80 degrees. That space has meaning. And while temperature does have a 0, 0 degrees doesn't mean the absence of temperature or no temperature. It's just a point along the number line that has the same spacing as all the other temperatures. Now, if we want to have a clearly defined 0, that's when we have ratio data. And that's where we have an absolute 0 that means literally nothing or none. An example of ratio data might be the length of a phone call or a test score or the number of children. If we said we got a 0 on a test or we have 0 children, that actually means nothing, the lowest amount possible. Now, these different levels of measurement can show up in different types of data. Let's scroll up. It's very important we understand the two different types of data, and the second one can actually be broken up into two subgroups. The first type of data is what is called qualitative. Qualitative data, which really focuses, again, on categories. No numbers. We're describing the qualities of something. So, for example, we might be talking about the type of car, or maybe some type of ethnic group. Those are the qualities of the data. That's qualitative data. The second type's the one we work with the most in statistics, and that is what is called quantitative data. And quantitative data is when we're looking at quantities. Quantitative data is either measured or counted. Really, what we're talking about is numbers. How many, how much, how far, how long. Some examples of these might be the number of students, or the distance to school. Quantitative data can even be divided up further. Quantitative data can be either discrete or, leave a space, continuous. Discrete data is data that is countable. 1, 2, 3, 4, 5. When we count things, we say we have discrete data. Generally, we don't get decimals with discrete data. Examples might include the number of shoes a person owns. You're not going to end up with decimal shoes. You're not going to have 1.4 shoes. Discrete data is countable. You count the number of shoes there are. That's contrasted with continuous data, which is measured, which means every decimal and every decimal in between those decimals is possible. Measured data, example, might be the length of a phone call. Or maybe somebody's height. That's continuous data. It's measured. Always we can have decimals. You can have half an inch. You can have half of an inch or a quarter. You can have an eighth of an inch. You can do all the decimals in between. That is continuous data. So that's the different levels of measurement we can do with different types of data. But we haven't answered the question of how do we collect our data, which is what we said we wanted to do at the beginning. So let's take a look at actual sampling of data. How do we collect it? When we collect data in a sample, we want it to be representative of the entire population. In order for it to be representative of the entire population, we need the data to be random to avoid any bias. In other words, we want all options to be equally likely to be included in our sample. So if random is best, let's take a look at a few random sampling methods. The first random sampling method is what we call simple random sampling. Simple random sampling is random selection methods such as random numbers, or drawing out of a hat. This is the idea of I assign everybody a number, and I pick a bunch of random numbers, and those people are included in my survey. An example is if I want to pick students, we could assign students a number. And pick random numbers to be included in the study. A second type of random sampling is what is called stratified random sampling. And this is when we divide the population into groups. Each group is called a strata, and then select a proportionate number of each group. Polling is often done this way. The idea is if we randomly survey 100 people or 200 people, we don't want those 200 people to be all of the same political party, otherwise we would get a biased sample. So we guarantee it by saying if my state is 40% Democrat, 35% Republican, and 25% independent, then using a random method, we will select, I said we wanted 200 people, so maybe we double the percentages. Maybe we'd select 80 Democrats, 70 Republicans, and 50 independents to be included in my sample. I have a proportionate representative of each group that matches the proportions of the state, and so my sample still is random, but I don't get the bias of only interviewing one party. Another type of random sampling also involves groups, but it's called cluster random sampling. Again, we're going to divide into groups. But this time, instead of selecting a proportionate number of each group, we are going to randomly select entire groups. So everybody in some groups are included, and everybody in other groups are excluded. An example of doing this might be a football stadium. And it has different sections in the football stadium. So instead of interviewing everybody in the stadium or random people through the stadium, it's easier just to hit one section at a time. So in the football stadium, sections E and G are randomly selected. And all fans from those sections are included. Cluster takes all people in each randomly chosen section, while stratified takes a proportionate group out of each group. The last random method we're going to use is called systematic random sampling. The idea behind systematic random sampling is we start with a random item or person, and choose every nth person after this. And that means like every 5th person, or every 12th person, or every 30th person. An example of this might be if I pick a random phone number, a random number in the phone book, and then I choose every 50th person after this until I circle back to the beginning. And go all the way through and back to the beginning and back to where I was, taking every 50th person. Those are our 4 random sampling methods that you should be able to identify for this course. There is a non-random method that is used quite a bit, and so we should at least acknowledge the non-random method called convenience sampling, which basically says use the results that are readily available. As an example, let's say I need to collect 50 data values for a survey, so I'm just going to interview people nearby me. Or maybe people within driving distance. Maybe the friends on my Facebook friend list. Something convenient and easy to get a hold of. It's not really random. And the problem with not being random is there are several drawbacks to not being random. I could have biased results. If I'm interviewing phone preference outside of the Apple Store, I'm going to get more iPhones. That convenience sampling is going to work against me. It may not be representative. Of the population. If I only interview outside of a school because it's convenient near my house, I'm going to get a lot more parents of young children than I will the general population. And then the drawback of that is the results may not be useful outside of the sample. I could conclude that such a percent of people prefer a certain type of music, but when I'm with a different sample or a different population, those results may not be useful. So those are some drawbacks to convenient sampling. We got to watch out for convenient sampling, though it is used more often than it should be. Take a look at the homework assignment that practices with random sampling and also some of these different levels of measurement and types of data. In class, we're going to do more work with random sampling, get really comfortable with the different types, and I'll look forward to seeing you then. Now that we know the basic vocabulary of statistics and know how to collect data, we're actually ready to start displaying some data. Our question for today is, how do we display data visually? And we're going to look at 2 main ways to display data. The first way is going to be with what's called a histogram. A histogram shows us frequencies over intervals. And a histogram can really give us an idea of the shape of our data. Let's do a quick example here. It's going to be easier to talk about a histogram with an example of a histogram. So here's a scale, 1, 2, 3, 4. Up the vertical axis, the y-axis is always labeled frequency. And then the x-axis is going to be some type of label of what we're actually looking at. Maybe we're looking at the number of TVs in a home. And I'm going to actually start at negative 0.5. I'm going to come over here to 1.5, 3.5, 5.5, 7.5, 9.5, and we'll end at 11.5. First box we're going to make 1 tall. The next one we're going to go up to 3. The next one we're going to start at 2. The next bar will start at 1. Then we'll skip a space and put a bar at 1. I'm also going to give this a title. Let's title this the number of TVs. And this picture is an example of what you would expect a histogram to look like. A couple things that I want to note. The bars on a histogram touch. They come down on the interval numbers. Not in between, but right on those numbers I labeled. And they show frequency in a range. In other words, if I color this second bar green here, what that second bar means is that there are 3 values, or 3 people who reported having between 1.5 and 3.5 TVs. Between 1.5 and 3.5 are the numbers 2 and 3. So the numbers 2 and 3 all went into that bar. Now, it's impossible to have 1.5 or 3.5 TVs. And that's what brings up the second point here, point B, if possible, and it's usually easiest with discrete data, never have a bar come down on a value. In other words, if I'm talking about the number of TVs, I don't want this to come down on 4 TVs. If a bar came down on 4 TVs, I wouldn't know if that 4 goes in the left bar or the right bar. So instead, I make sure my bars come down staggered from actual data values, in this case, by 0.5. And you also notice I took care to give a title to my graph and labels for the x and y axes. Title and labels are important. So now that we kind of know what a histogram is and what it looks like, showing frequencies over a range, let's look at how to make a histogram. First, we need to decide on the number of bars. Once we decide the number of bars, we'll use this nice little formula where we take the high number minus the low number and then divide by the number of bars. And then whatever that number is, we will round up. And that will give us the bar width, how wide each bar should be. Now, it's important to note we always round up. If it's 3.1, we'll still round up and the bars will be 4. In fact, if it's 3.0, we would still round up to have 4 bars of width 4. We always round up to the next number after this division. Next, we need to decide on the starting value. What I usually recommend we do to decide on the starting value is do 0.5 before the lowest number. In my TVs example, 0 is the lowest number of TVs, so I went 0.5 before that, so I'm staggered, and the bars won't come down on that. Then it's helpful to make a frequency table. Like we saw in section 1, with ranges. With the ranges that we found in parts A and B here. And we can use that frequency table then to build the histogram. So if that's the method, let's see if we can go ahead and actually do that with an example. The number of miles (20 students) commute to work is below. We are going to make a histogram with 5 bars to represent the data. And our data here is going to be 4, 6, 6, 7, 11, 13, 18, 18, 18, 21, 24, 26, 27, 35, 36, 36, 42, 43, 45, and 49. So for our bar width, we need to take the high minus the low divided by the number of bars. So the high is 49 and the low is 4. 49 minus 4 divided by the 5 bars is 9. Now it's exactly 9, so I have to round that up to 10 is my width. Always round up to the next whole number. Otherwise, your last values won't be included in the last bar. Now we can decide on our start values, or our ranges. So for our x values, to start with our graph, we're going to start half a unit before the low value of 4. So half before 4 is 3.5. And we're going to go up 10 to 13.5. The next range is going to start at that 13.5 and go up 10 to 23.5. Then we have 23.5 to 33.5. And I'm running out of space, so I'm going to scroll up a bit. 33.5 to 43.5. And 43.5 to 53.5. Those are our ranges. Now we just need to find the frequency inside each range. 3.5 to 13.5. There's 1, 2, 3, 4, 5, 6 numbers. 13.5 to 23.5. We only have 4 numbers. Then you see 23.5 to 33.5. There's 3 numbers. 33.5 to 43.5. There's 5 numbers. And 43.5 to 53.5, we see 2 numbers. Now that we have that frequency table, we're ready to build our histogram. Starting at 3.5, my next tick mark is 10 later at 13.5, then 23.5, 33.5, 43.5, and 53.5. Our frequencies go up to 6. 1, 2, 3, 4, 5, 6. The first bar is 6 tall. The second bar, touching it, is 4 tall. The next bar, touching it, is 3 tall. The next bar, touching it, is 5 tall. And the next bar, touching it, is 2 tall. And now my bars show the frequency within each of those ranges. Now I still need a title. We're talking about miles driven to work. It's a good title. Our x-axis is in miles. And then the y-axis, going from 1 to 6, always shows my frequency. And there's my histogram. Now with histograms, it's important not just to be able to draw the histogram, but we also need to be able to describe the shape of the histogram that we end up with. So a couple notes here on some vocabulary you can use to describe the shape of a histogram. And now with real-world data, it's never perfect. Histograms are never perfectly any of these shapes, but they tend to be close to one of these shapes. Not always, but generally, a common shape we'll see is what's called the uniform shape, where the bars are about the same. So just a quick sketch here. You might see bars that they're not quite exactly the same, but they're pretty darn close. We would say that histogram is uniform. They're all about the same height on all the ranges. Another word we should know is what's called a normal shape. The normal shape is taller in the middle and shorter on the edges. What a normal shape looks like is it generally starts short and gets taller until the middle, and then after the middle it starts getting shorter again. It's also called the bell-shaped curve, where it goes up and then back down. The opposite of the normal shape is what we would call the V-shape, and that is shorter in the middle and then taller on the edges. So that's when we have a tall edge that gets shorter, and then it comes back up and gets taller on the outside. And you can almost see that V shape right on top of those bars. In addition to the shape, we can talk about its symmetry. We say a graph is symmetrical if it's basically the same on both sides. So if we go tall and then shorter, it's going to be the same thing on both sides. You notice that's the same as the V shape. It's also symmetrical, the same on both sides. And we can combine these different descriptive words together to come up with a detailed description of a histogram. Then we have this idea of skewedness. Skewed means it's not symmetrical. And we describe the unsymmetrical part where the extra stuff is. Skewed right means it's not symmetrical because we have extra stuff, for lack of a better term, on the right. So that's where we're trying to be symmetrical, right? But then on the right side, there's all this extra stuff, and it kind of goes down a lot slower. That extra stuff means it's skewed right. And you might expect the last term then is skewed left, where the extra stuff is on the left. And that's where we've got all these extra little short bars on the left before it starts growing and giving us our what would be symmetrical shape. So that's histograms. We can draw them to show the shape of the data. We can describe them as uniform, normal, V-shaped, skewed, symmetrical. Really can help us visualize what our data set looks like. A second thing we can do, though, to describe our data visually is to draw what's called a box plot. And a box plot shows the spread of data with what is called the 5-number summary. Five-number summary is made up of 5 pieces: A, B, C, D, and E. The 2 easiest to find are the minimum and maximum. And then right in the middle of them is what is called, we'll put it on C, the median, or the middle when the data is in order. So the median cuts the middle of the data, and then we've got the top half and the bottom half. In the bottom half, we're going to find what's called Q1, or the first quartile. Which is the middle of the lower half. And similarly, Q3 is called the third quartile, which is the middle of the upper half. So the quartiles and the median really divide it into quarters. Now there's a little caveat with the quartiles and the median. We said they're the middle values, but if there are 2 middle values, what we'll do is we will add them together and divide by 2, giving us the middle of the middle. Once we find that 5-number summary, we'll usually represent it visually with what's called the box plot. The box plot splits the data into quarters. And to do that, we put Q1 and Q3 as the edge of the box. And then we draw whiskers out to the min and max values. And finally, we use a dotted line for the median. And so what we end up with is there's some number line down the bottom. And then floating above that number line is the box showing where the quartiles are, Q1 and Q3. Whiskers out to the minimum and maximum values. and then a dotted line for the median. And each part of the box represents a quarter, or 25% of the data values. The box then is the middle 50%, the whiskers are the outside 50%, and we can make some visual conclusions about how our data is spread out. Let's see if we can make a box plot. Going back to our example with the commute time, that list of numbers again for us was 4, 6, 6, 7, 11, 13, 18, 18, 18, 21, 24, 26, 27, 35, 36, 36, 42, 43, 45, and 49. Now, if this data was not in order, it would be essential as a first step to put the data in order. Fortunately, ours already is in order. We know there are 20 data values. So 20 cut in half is 10. We're going to have 10 below and 10 above. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cutting in half, 10 below and 10 above, sticks us right between 21 and 24. Because it's right in the middle, we add those numbers together and divide by 2 to get our median value, which is 22.5. Then we can go after our quartiles. Our quartiles are in the middle of the bottom half and the top half. Well, the bottom half has 10 values, so we're going to split 5 and 5, which sticks us right between 11 and 13. Again, because there's not one value in the middle, we'll add those together and divide by 2. 11 plus 13 divided by 2 gives us our Q1 equal to 12. For the upper quartile, again, we're going to have 5 data values on each side. Sticks us right between 36 and 36. When we add those together and divide by 2, the third quartile is 36. Also include our minimum value of 4 and our maximum value of 49. And we're ready to make our box plot showing the spread of our data. We should make every attempt to make this box plot to scale. So if I count by 6s, starting at 3, we'll have 3, 9, 15, 21, 27, 33, 39, 45, and 51. Notice those are about the same size apart from each other. My box is made from the quartiles at 12 and 36. So we connect our box. The median's a dotted line at 22.5. The whiskers go to the minimum of 4 and the maximum of 49. And we have our box plot. Of course, any graph needs a title, so we can title this commute time. And label the x-axis, maybe time in minutes. And we have our box plot. Now, normally the box plot would all be one color, but I did color coding to show where all the pieces came from in this example. And just like we can describe the shape of our histograms, we can also describe the shape of our box plots. And there's basically 3 ideas here. One is the idea of being spread out, where we have a wide range of values. This would be a big box plot. covers a large range of values. That means the data is not really close to each other, not close to the median, not really close to anything. It's all spread out. The opposite of being spread out is to be clustered together, where we have a small range of values. And this is going to give us a really tiny box plot. Everything's really close to each other. And often it's beneficial to split our description into the entire shape and the middle 50%, or the box. For example, I could have a box plot that looks like this. And we could say overall, the data is spread out, but the middle 50% is clustered together, because the box is small compared to the rest of the data. So that's what we're looking at today. Histograms and box plots. Practice making them, practice interpreting them, describing them. Take a look at some of them on the homework. We'll work with these a little bit more in class, and we will see you then. In our previous section, we took a look at how we could summarize data visually. But quite often, it's going to be useful to summarize data with numbers. So that's going to be our question. How do we summarize data numerically? And there's two things that we'll try and summarize numerically. The first one we're going to plant on for a minute here are the measures of center. Where is the middle of the data? And depending on our context, the measure of center will either be the mean, the median, or the mode. Let's start with the mean, or what people typically call the average. Now, if we're talking about a population mean, we will always use a Greek letter, and that's going to be the Greek letter mu. But if we're talking about a sample mean, we will use an English letter, which we will notate with x bar. And the formula for calculating the mean, I'm going to use x bar, but it works also for mu, is equal to this symbol, which we call sigma, x over n. And that symbol, that funny looking thing, means the sum. What this means is sum up all the x's, or sum up all the values, and divide by n, which is the sample size, or population size if we're in the population context. So for example, if I had the numbers 1, 3, 3, 4, 4, 4, 5, 5, and I wanted to find the mean of this sample, the numerator says sum up all the x values, or do 1 plus 3 plus 3 plus 4 plus 4 plus 4 plus 5 plus 5, and divide by the sample size. And if I count here, I see we've got a sample size of 8. So adding those all up, we get 29 over 8, which gives us a mean of 3.625, or the average is 3.625. Most students are familiar with that mean formula, but one tweak we can do to it, and we quite often have in statistics, it's not 2, let's call this C because we're still under mean, is if we have frequencies. So we've already seen one formula for the mean, the sum of the x's divided by the n. But if we have frequencies given to us where we know how often each number is used, the formula is going to tweak slightly. X bar is going to be equal to the sum of the x's times the frequency divided by the sample size. So if we have frequencies, we should know this formula. Let's do the exact same example we just did, but this time we're going to summarize those numbers by their frequencies. So first, I'll list out the numbers. The numbers that showed up were 1, 3, 4, and 5. But then I'm going to have another column that shows the frequency. I had a single 1. There were 2 3s, 3 4s, and 2 5s. What the sum says we need to do is first multiply the x's times the frequencies. So when we multiply, 1 times 1 is 1, 3 times 2 is 6, 4 times 3 is 12, and 5 times 2 is 10. And then what we want to do is sum this x times frequency table. So 1 plus 6 plus 12 plus 10 is 29. That represents the sum of the x's times the frequencies. And then we just have to divide by the sample size. Well, the frequencies tell us how many things there are. So my sample size is 1 plus 2 plus 3 plus 2 is equal to 8. So for my mean, again, we're doing 29 divided by 8 to get the exact same number of 3.625. But sometimes it's a lot quicker and easier if we have those frequencies given to us. That's the first measure of center. The measure of center of the average says if everybody was split up equally, they'd have this many in common. But quite often, the problem with the mean is one large value or one small value can throw off the mean significantly, which is why we might be interested more in the median or the middle number when they're first put in order. This way, one large or one small number won't have a dramatic impact on this measure of center. So for example, using our same data, the 1, 3, 3, 4, 4, 4, 5, 5, the median is going to be the value right in the middle. Well, if there's 8 values, the middle puts you between the 4 and the 4. And we know from our previous section when we made box plots, we would add those and divide by 2 to get our median value, which turns out here to be 4. And the big advantage of the median is that one extreme value does not impact the median as significantly as the mean. It's a little more stable. Now the third measure of center, and this is often used in categories or nominal data, is what is called the mode. The mode is the value that occurs the most often. And again, it's usually best for categories. If we're talking about the color of cars in the parking lot, we're not going to have an average of a blue point green car. That doesn't make any sense. But what we can do is say the most common frequent color car is blue or gray or whatever that most frequent one is. We can still look at mode in terms of numbers. We seem to be using this example data of 1, 3, 3, 4, 4, 4, 5. So let's keep using it. And what we see is the number 4 appears 3 times. It is the one that occurs the most often, so we will say that the mode is equal to 4. Those are our measures of center, the mean, median, and mode. But the problem with just measuring the center is it only tells us where the middle value is. It doesn't tell us kind of how all the rest of the data is behaving around the center. Is the data really spread out? Is it clustered close to the center? What's happening with the rest of the data? And that's why we also need some type of measure of spread. It tells us more than just the middle. It tells us how spread out the other values are. Not just where the middle is, but how's everybody else behaving around the middle. And the reason this is important is we can look at data such as these 3 data sets I'm going to put up here. And all of them, all of the following, have the same mean and median. The first data set's going to be 1, 1, 1, 5, 9, 9, 9. Both of that data set has a mean of 5. It also has a median of 5. But if I do another data set of 1, 2, 4, 5, 6, 8, 9, that data set has a mean of 5 and a median of 5. And if I do a data set of 5, 5, 5, 5, 5, 5, 5, that data set has a mean of 5 and a median of 5. There's no difference between these 3 data sets if I just look at the center. But the numbers are spread out quite differently. The first data set, the blue one, are spread out very far. The green one's kind of spread out evenly, and the red one has absolutely no spread in it at all. This is why we need a measure of spread. And the most basic measure of spread is what we call the range. The range tells us how much space there is between the largest and the smallest number. We take the large number and subtract the small number to see how far apart those extreme values are. So for example, with our data we've been playing with today of 1, 3, 3, 4, 4, 4, 5, 5, the range would be the big minus the small. 5 minus 1 equals 4. And so there is a space of 4 between all of these values. Now there's a problem with the range, though. The problem with the range is one extreme value could greatly impact. For example, if there was also a 27 on this data set, 27 minus 1 would sound like 26. There's a large range between the numbers, when most of them are actually clustered quite closely together. So this is why we need a different, better measure of center. And one measure of center that might be better is what we call the interquartile range. It's often abbreviated as IQR for interquartile range. And the interquartile range you could think about as the range of the middle 50%. What we'll do is we'll take the Q3 and subtract the Q1 value. subtract the quartiles, and we see the range of the middle 50%, or how spread out the middle 50% is, and then we're no longer going to be impacted by an extreme outlier that's way too big or way too small for the rest of the data. So for example, with our data of 1, 3, 3, 4, 4, 4, 5, 5, we already said the median was between 4 and 4. The first quartile then, Q1, is between 3 and 3, which is just 3. And the third quartile, Q3, is between 4 and 5, which is 4.5. This means our interquartile range is 4.5 minus 3, or 1.5. And that might be a little bit of a better measure of the spread because it's only looking at the middle 50%. The extreme outliers are not going to impact the interquartile range. However, we still have a problem. And that problem is this interquartile range formula only considers two values, the Q1 and the Q3. It would be nice if we had some measure of spread that considered all the values and how spread out those are. And this gives rise to the most important measure of spread, the one we'll use a lot in this class, called the standard deviation. And the standard deviation attempts to measure what we call the average distance a point is from the mean. How spread out is the data considering all the data values? On average, how far are they from the mean? Now, with a population, we will use a Greek letter for the standard deviation, and that's the Greek letter sigma. And with a sample, we will use the English letter S to represent the sample. The formula for the standard deviation kind of builds on this idea that we want the average distance from the mean. So if I took any point and subtracted the mean, that would give me the distance it is from the mean. The problem is some of these will be positive and some of these will be negative. So if I add them up, it actually adds up to 0. So to avoid the positive-negative problem, what we'll do is we'll square each of the values before we take the sum and add them all up. Then we'll divide by the sample size, which turns out with standard deviation, and when we derive the formula, it's not exactly the sample size we divide by, but we'll divide by n minus 1. And the reasons for the minus 1 are beyond the scope of this course, so you'll just have to trust me. To take an average distance from the mean with the standard deviation, we're going to divide by n minus 1. The problem that we still have, though, is we squared everything, so it's not really a true average. So to undo the square, we'll take the square root at the end of our formula, and we will say S is equal to that square root. And that is going to be an important formula for us in this course. Now, I do have one little caveat. Turns out that the formula for a population standard deviation is slightly different than S. The formula is. We're not going to worry too much about that different formula for the population because generally we always have a sample. We're always going to be taking sample standard deviations, which is this formula we've looked at here. So let's do an example. And let's start with a smaller example, and then we'll move to the bigger example that we've been seeing throughout this video. We'll start with the example 11, 13, 14, and 14. And I'll give you a hint. If you go through and calculate the mean of these values, the mean is going to be equal to 13. So what we'll do to get started is we'll list our values, 11, 13, 14, 14. And then we're going to have a column for every step along the way in this formula. The first step says take those x values and subtract the mean. Subtract 13. So 11 minus 13, I can even put a little 13 here. We're subtracting 13. 11 minus 13 is negative 2. 13 minus 13 is 0. 14 minus 13 is 1. And 14 minus 13 is 1. Then the formula says to square our values. So the x minus x bar, each of those values needs to be squared. Negative 2 squared is 4. 0 squared is 1. 1 squared is 1. And 1 squared is 1. Finally, the formula says to take the sum. So the sum of x minus x bar squared is equal to 4 plus 1 plus 1, which is 6. Now I'll jump to the standard deviation formula, which says the square root of the sum, which is 6, divided by 1 less than the sample size, which is 3. 6 divided by 3 is 2, and the square root is 1.41. Now, similar to our formula with means, if the data is given to us with frequencies rather than individual data numbers, we need to do a slight adjustment to our formula. So if we have frequencies, the formula will slightly adjust to s equals the square root of the sum of x minus x bar squared. But before we take the sum, we have to multiply by the frequency and then divide by n minus 1. So let's take a look at an example where we do it with frequencies. And let's use that data set that we've been using, where we know the x values were 1, 3, 4, and 5. And the frequencies of that were 1, 2, the number 4 appeared 3 times, and the number 5 appeared twice. Now, we already know that x bar, the mean, is 3.625. We would have had to find that first if we didn't know that. But since we do, now we'll make another column for x minus x bar. Taking the x, the number 1 minus 3.625 is negative 2.625. 3 minus 3.625 is negative 0.625. 4 minus 3.625 is 0.375. And 5 minus 3.625 is 1.375. Next, the formula says we need to square that x minus x bar. We're going to square each of these numbers. So 2.625 squared, and I'm going to round to 2 decimal places, is 6.89. 0.625 squared is 0.39. 0.375 squared is 0.14. And 1.375 squared is 1.89. Now, if we didn't have frequencies, we would just add this column up. But because we have frequencies, we need to take this column, the x minus x bar squared, and multiply by those frequencies. So the 6.89 needs to be multiplied by 1 to get 6.89. The 0.39 needs to be multiplied by its frequency of 2 to get 0.78. 0.14 times 3 is 0.42. And 1.89 times 2 is 3.78. And that's what we want to sum. We want to get the sum of x minus x bar squared times the frequency. And when we add up that column, you should end up with 11.87. Now we plug into our formula for S. S is the square root of that sum we just found is 11.87. Divided by 1 less than the sample size. You could add the frequencies together to find out that the sample size is 8. Or you might remember that because we've been working with this for quite a while. 1 less than the sample size is 7. So the square root of 11.87 divided by 7 is 1.30. So on average, these points are about 1.30 units away from the mean of 3.625. Gives us an idea of the middle and how spread out the data actually is. Now, the standard deviation is actually quite nice because it gives us a way to compare data based on how many standard deviations we are from the mean. Standard deviations measure distance from the mean. And in statistics, we will use a very important variable to represent the number of standard deviations we are from the mean. That variable is always going to be z. Z is the number of standard deviations from the mean. And we actually have two formulas that use z. They're both really the same formula. The idea is z is the number of standard deviations from the mean. So we'll take the value we're working with. We want to know how many standard deviations x is from the mean. Well, first we need to know the distance to the mean. So we'll subtract the mean, or x bar, and then we'll divide by s, or the number of standard deviations that is. That's our main formula for z. Now, sometimes we have the opposite information, and we want to know what is 3 standard deviations from the mean. We know z. We want to be 3 standard deviations from the mean. What value is that? And so we can solve this equation for x. And when we do, we get x is equal to the mean plus the number of standard deviations times the standard deviation. And so this formula, it's really the same formula, it's just been solved for x, will tell us the number of standard deviations is what value. Let's do some examples. Let's say for our data, 1, 3, 3, 4, 4, 4, 5, 5, we want to know how many standard deviations from the mean is the median. Well, we've already found all these important values. We found the median is equal to 4. Also, earlier, we found the mean was equal to 3.625. And also, earlier, we found the standard deviation is equal to 1.3. So if we want to find out how many standard deviations the median is from the mean, the medians are x, the mean's the x bar, and the standard deviation is s. So z, the number of standard deviations, 4 is, we subtract the mean of 3.625 and divide by the standard deviation of 1.3, and we find the median is 0.288 standard deviations from the mean. Or we could ask a similar question for the same data. What value is 2 standard deviations below the mean? We already know the number of standard deviations. So 2, that's actually going to be our z, the number of standard deviations below the mean. And because we want to be below the mean, we will use a negative number to make it below the mean. So we're looking for the x this time. What is that value of interest? So x is equal to the mean, x bar of 3.625, minus 2, because we have a negative 2 standard deviations below the mean, times the standard deviation of 1.3, and that gives us 1.025. Now, it turns out that we can say 95% of our data generally falls within 2 standard deviations of the mean. If it's more than 2 standard deviations from the mean, we say those values are unusual or extreme values. We call those extreme values outliers. And these outliers are values far removed from the rest of the data. For example, if I have the numbers 1, 3, 3, 5, 87, 87 is far removed from the rest of those values. It's an outlier. And the outlier can either be large or small. And we actually have 2 methods for calculating outliers, and they generate very similar results, so neither one is necessarily better than the other, but I want to show you both of them. The first one is called the interquartile range method. And the idea behind this is we cannot be more than 150% or 1.5 times the IQR from the edge of the box in the box and whisker plot. The idea is anything below the first quartile minus 1.5 times the IQR, or anything above the third quartile plus 1.5 times the IQR. Anything that's above or below those numbers becomes an outlier. So for example, let's say we've got the numbers 2, 3, 5, 6, 7, and 14. Now the median's right in the middle. But what we're interested in with the interquartile range is the middle below the median. The first quartile is 3. and the third quartile is 7. So the interquartile range is 7 minus 3, or 4. This means an outlier is anything below the first quartile, 3, minus 1.5 times the interquartile range of 4. That gives us 3 minus 6, or negative 3. Anything below negative 3 would be an outlier, which there's nothing in this data set below negative 3. But also anything above the third quartile, 7, plus 1.5 times the interquartile range. 7 plus 6 is 13. Anything above 13 becomes an outlier. And you notice 14 is right on the edge there. And so we will say, based on that, 14 is an outlier. It lies outside of the majority of our data. Now that's the interquartile range method. I said there's a second method. It's based on the standard deviation. The standard deviation method says that anything that is more than 2 standard deviations from the mean is an outlier. Which brings us back to that example that led into this discussion. So, actually, let's first define this clearly. Let's do anything below x bar the mean minus 2 standard deviations, or anything above x bar the mean plus 2 standard deviations is considered an outlier. So for example, we had our data of 1, 3, 3, 4, 4, 4, 5, 5. And we found out already that the mean of this data is 3.625. And we also found out the standard deviation of this data is 1.3. So an outlier would be anything below the mean, 3.625, minus 2 standard deviations. 3.625 minus 2 times 1.3 is 1.025. And we'll recognize there that we do have a value below 1.125, or 1.025. It's just a little below, but it is below. Here, 1 is an outlier. We also have to check above. So we'll do the 3.625 plus 2 standard deviations, or 2 times 1.3, which gives us 6.225. Nothing above 6.225, so the only outlier we have here is the number 1. So we've covered quite a bit in this video. We talked about measures of center, the mean, median, and mode to estimate where the middle of the data is. We talked about measures of spread to see how spread out we are around the mean or the center, using the range, the interquartile range, and the most important ones, the standard deviation. And then we also looked at some uses of the standard deviation to see its distance from the mean, finding outliers or identifying outliers. So lots to take a look at on the assignment. Take a look and practice a few. We will discuss them more in class. We'll look forward to seeing you then.